So Newton's first law of motion, this is the paper you're going to cut out. Cut off the motor, cut every box. And let's get started. All right. Newton's first law of motion, inertia. You've probably heard this before. An object at rest stays at rest, an object in motion stays in motion. Does that sound familiar? Yes. All right. That's Newton's first law. Okay? But that's very incomplete. That's a very incomplete description of the law and therefore very confusing. Okay? Go ahead and glue that in at the top. A more complete definition is that an object at rest stays at rest, an object in motion stays in motion, unless an unbalanced force is applied. Okay? That's a more complete definition. If you think about it, think about an object in motion that stays in motion. Can you think of an example of that? Because I don't know about you, but in my world, for example, if I go out on the football field and I kick a soccer ball, does it keep going and going and go? No. It slows and comes to a stop, right? That this idea is hard for us to understand. Okay? But it does work if you apply the idea of forces and the effect of forces have on motion. Okay? Newton is a very famous scientist and mathematician. Okay? So a little background on Newton. All right? You don't have to put this in your notes, but I just want you to know. All right? His full name, Sir Isaac Newton. Okay? What's up with the sir? What does that mean? Anybody know?
He was a dad.
Yes.
A knight?
He's a knight. He was knighted. All right? That means that the king or queen of England at the time made him a knight. What does that mean? Well, all it means is that he did something very important that made England more famous and wealthy, and or wealthy. Okay? He was a very important scientist and mathematician. Before him, whenever they discussed motion, they understood that force was involved, but they didn't understand exactly how. They couldn't explain how things move. Newton was able to explain why things moved the way they did. All right? Why they moved the way they did. Using these three laws that we're going to discuss. This is the first one. He calls it inertia. Okay? Now that Sir thing, okay, he was knighted because of that important contribution, as well. In that process of trying to describe how things moved, he came up with calculus. Which, if you don't know what that is, it's a very difficult form of math. Okay? So he actually came up with some pretty impressive stuff. Okay? His first law, he called it inertia. Okay? That's he got from the Greek. Okay? From the Greek. This is a Greek word. It means lazy. Inertia means lazy. If you translate it, lazy, flojo. All right? That's the literal translation. But he's applying that to objects in the universe. And he said that all objects in the universe are lazy. Okay? Well, that's what I'm going to explain, what that means. So first, I want to talk about objects that stay at rest. So find that objects stay at rest. Objects at rest want to stay at rest. I'm going to glue that in on the left side. The rest of the notes are going to be divided between the left side and the right side. So this is going on the left side. Okay? Objects at rest want to stay at rest. So what does it mean to be at rest?
Not moving.
All right. At rest means not moving, still stopped. Okay? So to clarify that. So If an object is not moving, it wants to stay that way. Okay? It wants to stay at rest. If I want to get the object to move, then I need force, but specifically unbalanced force. Okay? Now, unbalanced. Okay, what does balanced mean? Think about balanced. To be equal, okay? Imagine carrying a gallon of milk in one hand. If I want to balance that out, a gallon of milk in the other hand. All right? If I have a gallon of milk in both hands, I have balanced forces pulling on me. Okay? Does that make sense? So, if I want something to move, I need there to be an unbalanced force. Okay? So, just to emphasize, to change the motion of an object, force is required. So, force is required to change its motion. Now, to explain that a little bit, to give you a little more clarification, okay? This picture, the guy pushing on the box. If you take a good look at his face, he is putting a lot of effort into that. Okay? With paying attention to nothing more than the look on his face, what can you tell me about the box? All right. It has a lot of mass. Okay? That is one heavy box. Now, interesting little note. The more mass an object has, the more it resists a change in motion. Okay? Resisting the change. Okay? The more it doesn't want to change, the more mass it has. Okay? So the more mass it has, the more inertia it has, the lazier it is. Okay? So if this box has lots of mass, it has lots of inertia. Okay? Lots of mass, lots of inertia. Now, if you apply that to real life, personal example, okay? A few months ago, I was pregnant. I had lots of mass, okay? And in that state of having lots of mass, I was very lazy. My little rolly chair that I'm on here in the classroom, I never got out of this thing. I literally rolled around this thing in class all class period long. Okay? So, the more mass, the more inertia, the lazier you are. Okay? Now, an example that's kind of fun to talk about is the tablecloth being pulled out from underneath the dishes, and the dishes don't move. Have you ever seen that trick done before? Okay? It's one of those tricks where you're sitting, you're like, no way, and then you try it and all the dishes go crashing on the floor, right? Because there's a little few details to that to make it actually work well. But yes, it is completely possible, and it works just fine so long as you know the little tricks. All right? So, first of all, you got to make it happen really fast. Second of all, you need the tablecloth to be really smooth. Minimize the friction. Okay? The smoother that tablecloth, the easier those dishes and the tablecloth slide past each other. Okay? Also, have you ever noticed, if you flip over a plate, have you ever noticed the edge that it sits on the table? is rough, even though the rest of the plate is like glossy smooth. That's on purpose. So while you're like, cutting your meal, your plate doesn't move out from underneath you. All right, can you picture that? Cutting your meat and the plate's moving. You don't want that to happen. So you want there to be friction between your plate and the table. Okay? If you get heavy plates, lots of mass, lots of inertia, right? The more mass, the more inertia. So heavy plates, and you get them really smooth on the bottom, and you use a very smooth, silky tablecloth, it's really easy to do. Okay? And you have to move the tablecloth very quickly. And then, no problem. You can totally pull off the trick. Okay, in the lecture talked about air hockey and how that's a low friction situation. Well, here we have something different. It's the same idea, but this time the hockey puck has the air in it. So this has fans, it blows down, and so this rides on a cushion of air on the ground. It's kind of noisy, but, oops, but it's not air. There we go. And so it's going to move with constant velocity, okay? You get it moving, and it goes in a straight line at a constant speed. Straight line, constant velocity. Object in motion wants to stay in motion at a constant velocity. So constant velocity, single direction, constant speed, and it keeps moving that way because there's no friction to slow it down. So let's talk about objects that are in motion. Okay? According to Isaac Newton, an object in motion wants to stay in motion. Okay? Now, to be completely honest, that's kind of hard to believe because if ever you move an object, your life experience says it doesn't want to stay in motion, it wants to come to a stop. Okay? So, he explains that. Okay? But first of all, I need to clarify that in motion is a constant velocity. It keeps going and going and going and going. Okay? So, that constant velocity. What is velocity? Definition of velocity. Or a simple definition of velocity is speed and direction. Okay? So, if you have a constant velocity, the speed doesn't change. What else doesn't change?
Speed doesn't change, and the direction can change.
Very good. The direction doesn't change. Okay? The speed doesn't change and the direction doesn't change if you have a constant velocity. Now, you need an unbalanced force if you want to change that constant velocity. If you want it to not have a constant velocity, in other words, you want to slow it down, speed it up, or change its direction, then you need an unbalanced force to make that happen. Okay? So, in our life experience, any moving object always comes to a stop because there's unbalanced forces acting on those objects. And that force that normally does that is friction. The force that changes a an object's movement is usually friction. Okay? All moving objects usually slow down because of friction. So, get your highlighter, your one color highlighter. Highlight the word force. Force. All right? The force that changes an object's movement is friction. So the force of friction. The force of friction is what we're talking about here. Okay? So I want to give you guys a little picture of the lady with the ball. She catches that ball. She applies a force to stop that constant motion. All right, that ball is going to move with a constant velocity until something stops it. She's applying a force on that ball to stop it. Now, the last piece of paper, friction. Friction is a force that slows moving objects. Friction slows all moving objects. I should phrase that. The force that slows moving objects is friction. Okay, so highlight that. Friction is a force that slows moving objects. If you have very low friction, then the object moves much close. Movement is very similar to a constant velocity. All right, it appears to be moving with a constant velocity if there's very low friction. Okay, examples include hockey and air hockey. My guess is no one here has ever played hockey, but how many of you have ever played air hockey? Okay, the table blows the air up and the little puck goes around the table. You ever notice you hit that puck hard enough and it seems to keep going at the same speed? It bounces off the walls, but it just keeps going at that same speed. Notice that? That is a very good example of a very low friction where you have nearly constant velocity. And it always moves in straight lines. You notice that? It doesn't curve or anything like that. It moves in a nice straight line. Okay? So that's that constant velocity. A high friction situation is your tennis shoes on the floor. Friction is a good thing when it comes to your shoes. If there was no friction between your shoes and the floor, you couldn't stand up. You'd fall right on your butt.
Is that why they're made out of rubber?
Yep. That's why your shoes are made out of what they're made out of, to get lots of friction. Okay? If you ever have the opportunity to live in a place that gets snow and ice, you will experience this at least once in your life, for sure. You walk outside and you're just minding your own business and walking along, and all of a sudden, the next thing you know, you're flat on your back because you stepped on ice. It has happened to me more times than I can even remember. Okay? Because sometimes you don't even, because everything looks wet, all the ground's wet, and it happens to just be where you stepped was ice, and the next thing you know, you're flat on your back. Okay? Hopefully you didn't hit your head, because then it really hurts. Usually your butt hurts the most. Okay? So that would be a very low friction situation, because the friction that you're supposed to have with your tennis shoes wasn't there. Okay? Now, no friction. The only place we can really pull off no friction is in outer space. Okay? The reason why is because there's no air. Okay? Even if you have, for example, a ball flying through the air, it's not touching anything. It's not like touching the ground or touching somebody's hand or something, but the air is still slowing it down. Okay? So, there's no air in outer space, and in outer space, the zero gravity thing, you're not really standing on anything. So, tennis shoes in outer space, not much point because you're not really standing on anything. Okay? So, the no friction, because there's no air, if I take a baseball in outer space and I throw it, it keeps going forever in the same direction, at the same speed, forever, until some sort of force acts on it. The most likely force is going to be the gravity of like a nearby planet or something, but seriously, if it just keeps going, constant velocity, same direction, same speed, just going and going and going and going and going. It never slows down. Okay? So that happens in outer space just because there is no friction. Cool? All right. So if I kick a soccer ball here on Earth, I kick a soccer ball across the field, what is it that makes it stop? Friction. It's not gravity that makes it stop. It's the friction that makes it stop. Okay? The friction mostly with the ground, as it hits the ground and rolls. Okay? But if there was no friction, it would just keep going. So like a hockey, so playing hockey, you hit that puck. If there was zero friction between the puck and the ice, that puck would just keep going forever. Okay? Even if there was gravity. If there was no friction, which is obviously impossible to do, but if there was no friction, it would keep going forever. Okay? Does that make sense? All right.